All right, folks, so what we're going to be talking about are gas laws. And in particular, we're building off the knowledge from states of matter. So in particular, we're just going to be focusing our attention on gases and gases alone. All right, so first thing we need to have is a general knowledge of pressure, temperature, and volume. And so pressure, the key thing here with pressure is that it's a force exerted by a gas on a surface area. So it's force over area, okay? So if you want to think of it as like a formula, you can think of it as pressure is equal to force divided by area, okay? And we can measure that in a bunch of different things, such as millimeters of mercury, which is what we have there with the mmHg. We can have ATM, which stands for atmosphere, and we have kPa, which stands for kilopascals. And right here, what you will notice is I have the values set for what it is that they are equal to each other, okay? The one way in which we can measure pressure is by using what is called a barometer, and that measures what we call atmospheric pressure. And just so you know, we live under 1 atmosphere, in case you hadn't figured that one out. Okay. The other thing we need to know about is temperature. What is it? Well, it's the average amount of kinetic energy within an object. And we measure that using a thermometer. And in particular, for gases, we always want to measure our temperature in the unit of Kelvin. And the reason we want to do that is because Kelvin is an absolute temperature scale, meaning there are no negative numbers. The coldest temperature for Kelvin is 0 Kelvin. Everything else is positive. Okay, so there are no negative numbers with them. And that's going to be play a key role when we start talking about how we can predict what would happen to a gas if we were to change the pressure, the temperature, or the volume. All right. For the next thing, the last one is volume. Volume is just literally the amount of space an object takes up. We can either calculate it or we can measure it, and we usually measure that in milliliters or even liters. Okay, so let's talk about the relationship between pressure, temperature, and volume because they are interrelated with each other. The first one we're going to talk about is volume and temperature. Okay, and I need to go back here just for a second. All right. I do want to tell you that in order to solve for Kelvin, you take degrees Celsius and you add 273 to it. And the reason we do 273 is it's not just a random number that came about. It was actually done by looking at the volume and temperature relationship. So let's imagine this. Here's our question. All right. If you increase the temperature, what will happen to the volume of the gas? So if we increase temperature, the molecules move faster, and more than likely, because they're moving faster, they're going to cause it to expand. You've heard that. For example, hot air rises, and that means it is expanding. It is getting further away. So if you look right here at our graph on the left-hand side, you will notice that all of the gases that are being cooled down and looking at their volume and temperature, you will notice that they end up at this value of 273 degrees Celsius. That's where the idea of Kelvin came from. This is the lowest possible temperature. You'll notice that some of these lines are dotted, and the reason they're dotted is because of the fact that, ladies and gentlemen, they do not end up, we cannot measure their volumes. They literally become solids, okay? So if that makes any sense, so they're no longer gases anymore. They become liquids and solids, okay? Now, so what type of relationship exists here? If we look at the graph here, we have volume over here on the left-hand side. We have temperature down here on the x-axis. So we can see that we have what is considered to be a direct relationship, meaning if the temperature goes up, the volume goes up. If the temperature goes down, the volume goes down, all right? So there's a direct relationship between the two. When we talk about pressure and volume, all right? So let's ask, if you reduce the volume of a balloon by squeezing it, what happens to the volume? Or I should say, the pressure is what I should be saying here, all right? So if the volume is, if we take the balloon and we squeeze it, the volume's getting smaller and smaller and smaller. And if we're getting smaller and smaller, we're getting the particles closer and closer together. And as you can see here in my diagram, on the left-hand side, we've got a pressure of 1 atmosphere and a volume of 1 liter. And then what we do is we decrease the volume by half. When we do that, the pressure goes up by a factor of 2. It doubles. And same, if we take again and reduce the volume by half again, we then again double the pressure. So it would appear, ladies and gentlemen, that we do have a relationship between pressure and volume, and that would be inverse. As one value goes up, the other value is going down. Meaning, if the pressure right here, ladies and gentlemen, is starting up here, and we were to reduce the pressure, that means that the volume would start to, for example, increase. Okay, so if volume is increasing, all right, that means that the pressure will be decreasing, okay? Meaning if the size of the container is getting bigger, it has more area to hit, so the pressure is going to get less and less and less, and vice versa, okay? The other relationship is pressure and temperature, all right? And if, for example, we were to increase the temperature of gas, what's going to happen to the pressure? Well, if the particles are going to move faster and faster and faster, they're going to have more force. And when they collide with more force, that means they're going to have more pressure, especially if, ladies and gentlemen, the volume is held constant, okay? And so you notice how pressure and temperature and volume can all be related to each other. So in this particular instance, pressure and temperature are a direct relationship, meaning if we increase the temperature, the pressure will increase, and vice versa. If we decrease the temperature, the pressure will decrease. Give you an example. Has anyone here ever used, for example, those air cans that you can clean like computer components with? Well, as you continue to use it, what ends up happening as the gas comes out, the pressure is reducing and the temperature of the can gets very, 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 very cold, okay? And so that, ladies and gentlemen, is a great example of pressure and temperature.